If you discontinue watching this video, please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn particle physics. Today, Majorana's mystery, and after we've done that, we're gonna do standing yoga. And if you participate in the standing yoga, then it's at your own risk. And this is part 2 of Majorana's mystery. It is about, I don't know what Majorana's mystery was. It is about if there's more matter than antimatter, and the standard model of particle physics says there's the exact same amount of matter as antimatter. Now there were now the photons, and the photons, they are themselves their own antimatter. Today's standard model of the workings of matter predicts that absolutely every particle has an antiparticle. A proton has an antiproton with a negative charge. There's a negative charged proton and antiproton. There's the electron and there's the positron. There's a positive charged positron and a negative charged electron. The chargeless, massless photon, for example, is its own antiparticle. And two photons annihilate themselves on the rare occasions they interact. We're saying if the photon itself is its own antiparticle. And we had something about neutrinos, there was something like that. And now leptons, I think, also. If neutrinos are indeed their own antiparticles, their workings might also account for the matter-antimatter imbalance in our universe, provided also that as yet undiscovered heavier stereo neutrinos exist. The idea is that neutrinos exist, different of them in different stages, and something like that. But therefore these most real in advanced stages of neutrinos has to be found first. Each of the three types of neutrinos seems to have an anti-neutrino equivalent that participates in particle reactions very differently. Okay. According to an idea known as leptogenesis, in the first microseconds after the Big Bang, the young, hot universe contained extremely heavy, unstable stereo neutrinos that soon decayed, some into leptons and the remainder into their antimatter counterparts. But because the neutrinos represent an ambiguous state that was both matter and antimatter at unequal rates. Okay, well, first let's start at the beginning to understand the sense. There was a Big Bang, and in the first microseconds of very short for time, there were a lot of neutrinos. And they were decaying then into leptons and the antileptons, probably. But because the neutrinos represent an ambiguous state that was both matter and antimatter, so if the neutrinos are their own antimatter, if they had the state in the time when the neutrinos were going to leptons and neutrinos at unequal rates, because the neutrinos were themselves matter and antimatter, they did not become leptons at the same rate. Let's read on. This neutrino CP violation need only be tiny, 1 part in a billion. But it would mean that when the matter mopped up all the antimatter, enough leptons remained to transform into protons and neutrons that went on to form stars, galaxies and planets. Okay, there was no matter and antimatter, and that is the CP violation, that there's not the equal amount of it. But it would mean that when the matter mopped up all the universe, all the antimatter, enough leptons, which had to come out of neutrinos after this theory, went on to remain to transform into protons and neutrons. Out of them now the stars, galaxies and planets came. Okay, we're saying there were a lot of neutrinos and neutrinos. Neutrons are inside of an atom. So there are protons and electrons and neutrons. And we're talking now what is inside of these protons, inside of these electrons. And inside of them there are the neutrinos. And different types of neutrinos can come together to form a proton. And now a proton together with an electron, that is somehow when it starts to become an atom and then an element. Something like that, we don't really get it, but we're talking about something like that. Okay. Who are now these leptons? Let's read it again. The young hot universe contained extremely heavy unstable sterile neutrinos that soon decayed into leptons and the remainder into their antimatter counterparts. Do the antimatter counterparts of the neutrinos or antimatter neutrinos and the counterparts of the leptons? I think that means from the context of the antimatter to the neutrinos. But because the neutrinos represent an ambiguous state that was both matter and antimatter at unequal rates, it would be only necessary to be that there's a billionth of difference. That billionth would be enough matter or enough things to form galaxies, stars, and planets. Let's read on. So far, experimentalists haven't uncovered any convincing neutrino CP anomalies, although it may be that we just haven't measured with enough sensitivity yet. Okay, we didn't found that there is more neutrino than antimatter imbalance, that there's more matter than antimatter. But one reason is maybe that the instruments are not sensitive enough. We're talking about a billion of difference. But I don't get it. At another place they said it is 60, 70% or 30%. That would be a big difference between matter and antimatter. And all the last 2-3 pages we're just talking about, we can't even find the difference. But they seem to be sure that there is one. I don't, maybe I somewhere lost track. But there is another test at least of whether neutrinos are Majorana particles. Let's read it again. Ettore Majorana had a talent for enigma. The mercurial Italian's sudden disappearance somewhere en route from Palermo to Naples in the spring of 1938 still excites lively discussions. The particles that bear his name are now less enigmatic. Their origin lies in a seemingly innocuous modification Majorana made to Paul Dirac's equation that established the existence of antimatter in 1928. In Dirac's original formulation, only electrically charged particles had antiparticles. Majorana's tweak produced antiparticles for charged particles too. Okay, that was it. But everything has an antiparticle with the opposing charge. The electron has the positron with the opposite charge, negative electron, positive positron. But now Majorana said there are other particles with neutral, and they are then themselves their own antiparticles. They were not listed in Paul Dirac's in the 1920s equation because that was just about charged particles. Electron, so it has a positron. But now we're talking about neutrinos, maybe leptons and so on. They are themselves their own antiparticles, is the idea, if you understand it correctly. They are themselves because they already have no charge. If they encounter each other, they annihilate each other. If they are, we would expect to observe a process known as neutrinoless double beta decay that the standard model frowns upon. Okay, we would have neutrinoless double beta decay. In normal beta decay, a neutron changes into a proton and emits an electron, and an electron antineutrino. Okay. By beta decay, there's a neutron existing, and it then decays into a proton and an electron, and also in an electron antineutrino. Some nuclei can undergo 2 such decays at once, in which case we would expect 2 antineutrinos to be emitted. If these antineutrinos are identical to neutrinos, however, they would annihilate each other on emission, and the reaction would produce just 2 protons and 2 electrons. Okay. By beta decay, they're in neurons, and they're getting to protons and electrons and an electron whatever. Now, and if some 2 reactions happening at the same time, I don't get what. There are now 2 of these there are 2 protons, 2 electrons, and 2 anti-neutrino something. Now, and if there are these 2 processes happening at the same time, and there are 2 anti-neutrino things, they annihilate each other, and we cannot find them. So the idea is here that if there is, during beta decay, when a neutrino is coming to a proton, the electron, and an antineutrino. antineutrino. So when a neutrino decays into a proton, an electron, and an antineutrino, then you would have had. But what if at that second two things happening at the same time, two decayings, I don't get what. Then we're having two protons, two electrons, and two antineutrinos. And the two antineutrinos annihilate each other, and we can't find them, we find only the two protons and the two electrons. If these antineutrinos are identical to neutrinos, however, they will annihilate each other on emission, and the reaction will produce just two protons and two electrons. Neutrinoless double beta decay is the smoking gun that neutrinos are Majorana particles. Okay, that is it. I think it is that they can do beta decay and they can find two protons and two electrons. And that makes it then very likely that is, I don't know on what state we are. If it is a hypothesis, I don't know what we're basically talking about. But that is the idea. If we find two protons and two electrons, when we're making two at the same time, I think we're doing it intentionally two at the same time. Just two beta decays at the same time. And we don't find our antineutrino. That means that they have annihilated themselves. That means that they are themselves their own antimatter particles. Get it? We're having a neutrino, one, and we're making a decaying intentionally. We can do it, I don't get now. We're having a proton, electron, and a neutrino. Perfect. We find a proton, electron, and an antineutrino particle. And now we're doing that twice. We're doing two neutrinos are letting we decay, and we're getting two protons, two electrons, and nothing. And that means by the first one we found an antineutrino particle. Now we're finding no one. That means there were two. We had done it twice. There were two. We know when one, two, but there are no two. That means these two have themselves annihilated themselves because we can't find them. That means they are themselves their own antimatter particle, and they annihilate themselves as soon as they react, find each other, whatever. And that means the antimatter balance would work for neutrinos because they are antimatter themselves, their own antimatter particles. That says Alan Poon at Lawrence Berkeley National Laboratory in California. It would give lots of tips to theorists on how to update the standard model, and it ties back to the very early universe, how we got more matter than antimatter. How now, eh? Because the antimatter part had annihilated themselves, but it had the matter to... Back in 2002, a Russian-German collaboration claimed to have seen neutrinoless double beta decay, but no other experiment has replicated the results. Okay, there was an experiment where people said we found two protons, two electrons, and no antineutrinos. It's own antimatter thing. We did it, but no one could replicate that experiment, and that isn't necessary for science, so it isn't proven yet that is the case. More recent findings show that if neutrinoless double beta decay exists at all, it is extremely rare, perhaps vanishingly so. Why is it rare? Nevertheless, so great would be the price of observing it that it remains the object of multiple research projects. In 2022, the latest LEG&D Large Enriched Germanium experiment for neutrinoless decay is starting up at the Gran Sasso Laboratory in central Italy. Where is the picture? So where we're trying to do it. Okay, the whole thing what we're doing is we're having a neutrino, we're letting it decay, and we're getting out a proton, an electron, and an antineutrino. And now we're saying let's do it twice at the same time. And now we're getting two protons, two electrons, and nothing. And that means these two antineutrino things have annihilated themselves. Neutrinos are their own antimatter particles. The antimatter, I don't get what that means. But we could not replicate that experiment, and it seems to be difficult to do that experiment. It seems to be happening not always. I don't get it, but these people are trying to do that with that thing. It was a particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics. If you stay here and participate in the 1 minute standing yoga, we don't have time yet. Then it's the downwards. Having your feet standing together, and we're doing the ego swings. Breathe in and lift the arms up. Down the arms down. In and up. Out and down. In and up. Out to the side. In and up. Out to the other side. In and up. Breathe in and go up onto tiptoes. And out, we're going down onto the pillow. Breathe in, then the right leg. Breathe out, stretch left leg. In and change. Out, stretch right leg. In and to the middle. Out and down. Breathe in and cover both arms up again. Breathe in and lean back, drop the shoulders together. In and up again. Out again, back with the arms. In and up. Over, cross the arms, intertwine the fingers, breathe in, reach high. Breathe out, reach to the front. In, up, breathe in, and over, cross the other way around. Out in front, reach in front, out of the back, breathe in, breathe out, breathe in, up. Out and back with long arms. In and up. Out the arms down, breathe in the arms up. Bring the hands to touch and lower the hands down to heart center. That was 1 minute yoga. I thank you very much and until next time.